Welcome. We are going to move on from triangles to quadrilaterals, so to polygons with 4 sides. And just like with triangles, we are interested in some special cases and what they mean for our calculations of angles. And here it really helps to understand why these special cases have the special properties that they do. Of course, you can simply look up and memorize the special properties of, for example, a parallelogram, but it is much more satisfying to understand why all of those properties go together. So let's start with any random triangle, and we draw the median. So we go from one vertex to the midpoint of the opposite side. Now we're going to do something special. We rotate this triangle around this point by half a turn. And the result is now a 4-sided polygon. Now what can we say about this polygon? Well, the first thing, of course, will be that it has point symmetry. After all, we got the second half by rotating the first half around this point. What else? Well, we know that some of its sides will be equal. After all, this side was just this side rotated by half a turn, and this side was just this side. So its opposite sides are equally long. Then let's look at the diagonals. We started already with this diagonal. It used to be a side of our original triangle, and this point cut it in half. If we look at the other diagonal, the blue one here, then this part is the same as this part. So this diagonal is also cut in half by this midpoint. So basically the diagonals divide each other in half into 2 equal parts. Then remember that we rotated our triangle by 180 degrees. When you rotate a line by 180 degrees, the new line will be parallel to the old one. So these 2 sides are parallel, and for the same reason these 2 sides are parallel. And this is what gives the shape its name. It's called a parallelogram. And finally we'll take a look at the angles. We started with this triangle, with this angle, and we rotated it like this. So that means that this angle here on the other side is the same as this one. Now we could have gotten the same shape if we had started with a different triangle, with this angle, and rotated it like this. So for the same reason as the red pair, this pair of blue angles is also identical. So the conclusion is, in a parallelogram, opposite angles are equal. And you can imagine that this will be something to keep in mind when we solve puzzles involving angles. So we get a parallelogram if we rotate any triangle around the midpoint of one of its sides, like we just saw. What if we take a special triangle? So we take an isosceles triangle with 2 sides equal, and we draw the median from the vertex angle. From the vertex angle to the midpoint of the base. And this is a special case because now the median is perpendicular to the base. The isosceles triangle, because it has 2 equal sides, has line symmetry, and this red line here is the axis of symmetry. So now we rotate it, like before. We get a parallelogram again, but this is a special case called a rhombus. And the ways in which it is special all follow from the fact that we started with an isosceles triangle. These 2 sides were equal. So they're also equal to these 2 sides. So that means that all the sides of this shape are equal. All the sides of the rhombus are equal. This line was perpendicular to this line, and they have now both become diagonals of the rhombus. So the diagonals of a rhombus are perpendicular. Then, because of the line symmetry of the isosceles triangle, this diagonal perfectly cuts these blue angles in half. And for the same reason, also isosceles triangles here, this diagonal, the black one, cuts these purple angles in half. Finally, because it is made up of isosceles triangles that all have line symmetry, the rhombus itself has line symmetry. These 2 triangles are each other's mirror image, and the line of symmetry, the axis of symmetry, is this diagonal. And these 2 triangles are each other's reflection in this diagonal, in the red diagonal. So the diagonals are axes of symmetry. So the rhombus is a special parallelogram made by reflecting a special triangle, an isosceles triangle, in the midpoint of its base. you already know another parallelogram that we can build out of a special triangle, and that is the rectangle. It starts from a right-angled triangle, and we rotate it around the midpoint of its longest side. This angle was 90 degrees, so this angle is 90 degrees as well. Now, a good way of testing yourself is, can you explain why we can now be absolutely sure that the other two angles of this parallelogram will be 90 degrees as well, and not, for instance, 91 degrees and 89 degrees? See you next time.